There are four numbering systems that you will see when programming: binary, decimal, octal, and hexadecimal. Binary is a base 2 system with only two numbers in it, 1 and 0. This is what computers use in machine language. Decimal is the base 10 number system that humans tend to use. Octal is a base 8 number system that's used to represent binary data more efficiently. This was especially relevant in older computer systems and is still sometimes used for tasks like understanding file permissions in Unix-like operating systems. Hexadecimal is a base 16 number system. Hex equals 6, deca equals 10, so hex plus deca equals base 16, and is primarily used when dealing with low-level operations like memory addresses, network addresses, or raw binary data. Additionally, you will often see it used to define color codes, especially for web developers. On our worksheet today, Number Systems and Conversions, we're going to look at how each of the other number systems relates to our decimal number system and practice converting numbers into each of the number systems. I'll do one example for you from each section on the worksheet, and you'll be responsible for doing the rest. Please make sure you show your work for each problem, or you will not receive credit for your answer. Binary numbers are represented in sets of 8 digits, and each of the places corresponds to a specific number. Let's look first at the decimal to binary conversions. Across the top of the section, please write the following numbers: 128, 64, 32, 16, 8, 4, 2, and 1. For the first conversion, we need to put zeros and ones in each column underneath the number we wrote. The values that go with each one should add up to the decimal number when we're done. For 16, there are 0 128s, 0 64s, 0 32s, but 1 16. After that, we've already reached our decimal number, so the rest will be zeros. This gives our final binary number of 001 0000. Converting binary to decimal is exactly the opposite. We're going to add up the corresponding numbers for each one to get our final decimal value. The first number in the binary number is a 0, which gives us a value of 0. The second and third are also zeros, giving us two more zeros in our values. Next, we have a 1 in the 16th column and a 1 in the 8th column, giving us two more values for our calculation. These are followed by a 0, a 1 in the 2's column, and a final 0. All added together, our values add up to 26. Octal and hexadecimal are a little more difficult than the two number systems we just looked at. We're going to have to do a bit more complicated math to reach our decimal values for both number systems. The first thing we do in both number systems is to write down our decimal value, which for our octal problems is 497. In octal, we then divide the value by 8, which is the base number for the system. We end up with 62.125. We will save the 0.125 for a future calculation and then do 62 divided by 8, which gives us 7.75. Again, we're saving that 0.75 for a future calculation. So our final main number is the 7 that we have at the end of our calculations, since we can't divide that by 8 any further. Next, we need to find the last few digits for our octal value. After working left to right like normal in math to get our main number, now we work backwards to get the last two values. So 0.75 times 8, again, we get that 8 from the base value of the number system, gives us a 6, which will be the second value in our octal value. Going back to the left one more time, we use the 0.125 times 8 to get our last number, which will be 1. Our final octal value for the decimal number 497 is 761. Hexadecimal works in a similar fashion. The first thing we do is write down our decimal value, which is 1055. In hexadecimal, we then divide the value by 16, which is the base number for the system. We end up with 65.9375, and we're going to save that 0.9375 for a future calculation, and then do 65 divided by 16, which gives us 4.0625. And again, we're saving the 0.0625 for a future calculation. So our final main number is the 4 that we have at the end of our calculation, since we can't divide that by 16 any further. And to find the last few digits for our hexadecimal value, we're going to work backwards. So 0.0625 times 16, again, we get the 16 from the base value of the number system, gives us a 1, which will be our second number in our octal value. Going back to the left one more time, we're going to use the 0.9375 times 16 to get our last number, which is going to be 15. The problem with getting 15 is that if we write it in our hexadecimal value, we end up with 4,115, which is way higher than it should be. The 15 ends up looking like the numbers are from two separate sections of the problem. Instead, in hexadecimal, numbers that have 2 digits are converted to letters. So 10 equals A, 11 equals B, 12 equals C, 13 equals D, 14 equals E, and 15 equals F. We stop there because 16 divided by 16 would bring us back to 1. So our final hexadecimal value for the decimal number 1055 is actually going to be 41F. Now you'll be finishing the rest of the problems on the worksheet. Good luck.